When last we spoke, we had created a description of the velocity instantaneous. The velocity originally defined on average, and here's my summary here. Once I've defined the displacement, which is the change in position, acknowledging that mine is a universe of change, I describe the rate of change of position on average. I have some initial measurement of position, final measurement of position. I acknowledge I have no idea what goes on between those two measurements. It takes a certain amount of time, or there is time between those measurements. Maybe I make a measurement, then I have a sandwich, and then I make another measurement. There's some interval of time. And in that interval of time, I define the velocity on average. Well, I'm unsatisfied by that. I think I could do something more sophisticated. So I define for myself the velocity at any instant as the instantaneous rate of change. And I impress upon you, I cannot enough impress upon you, that there is really no difference between delta x over delta t and dx over dt, except the interval is very, very, very small. So small, in fact, that it is infinitesimal. And there are some, want to say theoretical, but that's not what you say in regard to math. There are some sort of technical math aspects to that, some special features when you imagine intervals to be quite small. And so there are techniques of calculus that will allow me to determine, through some black magic mathematics of calculus, what is the velocity as a function of time if I know the position is a function of time, the rate of change. Well, so now I observe the change of my universe in two contexts: the fact that the positions change, and also that the velocities may in fact change. If I make two measurements of position, that gets me a velocity on average. If I make two other measurements of position at some later time, I get the velocity on average, and I discover through experiment they are not the same. And I acknowledge the fact, the rather obvious fact in my universe, that the velocity of a particular object might change over time. That is, there is a rate of change of velocity to be discovered. And that discovery is quite easy to realize. There must be some quantity that I could draw. Well, I say this. These quantities are all by my definition. I had said when I invented delta x, final position minus initial position, I just made that up. The description is by definition. And so in the spirit of making up anything that I want, imagine that I consider how much the velocity changes in some interval of time between measurements. So in order to get a single velocity, I would have to make two measurements of position. To get a second measurement of velocity, I would have to have two more measurements of position. So I've made 4 measurements of position, all the while also making measurements of time in whatever way that I choose. And I devise this quantity that is the rate at which the velocity changes. Quite naturally, this thing is going to have some units. In the numerator, meters in a certain number of seconds, and in the denominator, a certain number of seconds. So it is meters per second, which when you say it like that is quite sensible. The velocity has changed by a particular number of meters per second in every second that the velocity changes. But we don't write it this way. For our convenience, we write the acceleration instead as meters per second squared. As we go along, I guess, there's a thing that happens that the units that we use to describe our measurements become more and more sophisticated and more relevant. I'm going to be looking at, for example, some problem solution that I'm asked to do. There might be a great many figures involved, and I'll look at their units to determine what is what. And to me, meters per second squared is almost, I don't see it as meters and seconds, and a 2 there is the square. It's an icon of a quantity known as the acceleration, which quite naturally I'll give the symbol A, acceleration. And the acceleration on average will be defined just as the velocity was defined on average, as the change in the velocity divided by the time in which the velocity changes. It's just that simple. The acceleration in meters per second squared. I similarly have a problem here with notation, in that this is the acceleration on average, and I should consider that. And perhaps I would make that notation by putting a bar over the A. But I also appreciate that acceleration is defined in terms of the velocity, which is defined in terms of the displacement, and is therefore also a vector quantity. So perhaps I should be writing my acceleration with a vector harpoon. I realize I'm stating this probably for the 3rd time, but I have a bad habit of when I appreciate that a thing is a vector, I don't bother with the harpoons so much. But you know what? For giggles, I'll just add them here. Here's a harpoon on the A to indicate that acceleration, like velocity and like displacement, is a vector quantity. And here is velocity, also a vector. If I define acceleration in terms of a vector, then it inherits, in many cases, not all, but it inherits that vector quality to it. Which means, like velocity, acceleration has a direction, but it is not so simple in the case of acceleration as it is with velocity. For velocity, the direction of that quantity is the direction that you're moving. It's quite obvious. And we know that when we handle vector quantities mathematically, we often draw them on the page as arrows pointing somewhere. And the direction of the velocity vector is an arrow pointing in the direction of the thing is moving. It is quite simple. It is not so simple to interpret the direction of the acceleration vector, because the acceleration vector points in the direction that the velocity changes. The acceleration vector points in the direction that the velocity changes, and that's a curious thing. So I'd like to consider that for just a moment with a little bit of vector exercise that perhaps you've seen before, but now since it's of issue, I'll talk about it now. Vector addition is quite simple. If I had two velocity vectors and I wrote them in I hat, j hat notation, adding vectors in that notation is simple. You add the x and you add the y. So if I wanted to add two velocity vectors that had x and y components, I would simply add the x components and add the y components. But as we learn about those vectory things, we very often draw diagrams of arrows showing vector addition. For example, imagine that I have a velocity vector in two dimensions that looks something like this. Now, I just made that up. It's just some velocity vector v, and I'll call it v1 because I'm going to draw a second one. Here's the velocity vector v1 drawn off at some arbitrary angle thusly. This vector points in the direction the thing is moving in that instant. The length of the vector that I've drawn is scaled to that velocity. If I were to draw a shorter vector, it would be a lesser magnitude of velocity. If I drew a longer vector, it would be a larger magnitude of velocity in linear proportion. But there's the velocity vector v1. Imagine another vector v2 that I'm curiously going to draw in such a way that the tail of that vector v2 starts at the tip. Now, a thing about the definition of vectors is the location of their tails is irrelevant. I can draw them anywhere I want to in the plane of the board. I have drawn these two vectors conspicuously sitting one atop the other, but I could have drawn them, if I chose, I could have drawn them one in one corner of the board and one in the other corner of the board, and they would be the same vector, because a vector is by loose definition, a magnitude and a direction. So when I draw the vector of a particular length and it points in a particular direction, that is the definition of the vector. It matters not where the tail of the vector is. In this case, just for a laugh, I happen to put the tail of this vector at the tip of the other vector. Vector addition, by graphical definition, is the vector that points from the tail of the first vector to the tip of the last vector. This vector that I've drawn here is vector 1 plus vector 2. And what I mean is velocity 1 plus velocity 2. That is how we graphically define vector addition. That's what vector addition is. And when we learn about these things the first time, it is quite common to go on with vector addition, and vector addition, and never mention vector subtraction graphically. Because after I draw this diagram, I realize from this diagram that in order to add vectors v1 and v2, I'll simply add their x components and add their y components, and I'm done. The graphical version of it is equivalent to the algebraic version of it. Add the x components, add the y components, you're done. And so then once you make that realization, how then should I do vector subtraction? Well, that's easy. Subtract the x components, subtract the y components, and you're done. So I don't need any graphical representation of vector subtraction, except right now in this moment. Because in order to calculate the change in velocity, delta v, I have to subtract vectors. What direction does that delta v vector point? Let's investigate using these two vectors v1 and v2 that I've already drawn here. Consider this algebraic expression that is completely obvious, that delta v vector is equal to v2 vector, which I will imagine is the final vector, minus the initial vector, which is v1 vector. It's a difference between two vectors. I'm leaving the harpoons on now. I was just chiding myself for not using harpoons as often as I should. I'm using the harpoons now because it is the vectorness of these things that matters to me. I have to really ram home the idea. These are vector quantities. Well, there is a vector equation written. A vector equation is different than a scalar equation. If I say distance is velocity times time, that's not what I meant to say. If I say distance is speed times time, those are all scalar quantities. They're just numbers. That's an algebraic equation, just like the ones that you've been using your whole math career up until this point. But this here is a vector equation. Oh no, they're special now. Well, a way in which it is not special is that the rules of algebra and algebraic manipulation still apply here. Even though this is a vector equation, I can quite casually take the v1 that's hanging on here with a minus sign and add it to the other side of the equation. That is the change in velocity vector delta v plus the initial velocity vector, which I'm pleased to call v1, is equal to v2. When I'm dealing with vector quantities, it's okay to do what you feel. I can just do algebra the way I normally do algebra, and the vectors drawn this way and this way, they're all taking care of themselves in the rules of familiar algebra that I already know. And it's a little strange, but I would like to ask you to humor me when I take these two terms here to the left of the equal sign and reverse them. I want to take these two terms and reverse them. It doesn't change anything really, but it changes the idea for me and allows me to illuminate something that you might not immediately see. By reversing these terms, I have v1 vector plus delta v vector is equal to v2 vector. Believe it or not, this makes it possible for me to describe the direction of the change in velocity vector, because what it's saying is take v1. Well, I know what v1 is here. Refer to my previous diagram. That's v1. Now I have a task here working on the board that's a bit difficult. I need to redraw v1 over here. I need to redraw v1, which means I have to draw, like literally with my marker, this is the challenge. I have to draw the exact same length and the exact same direction. I have to redraw v1, and it has to look identically the same, which as a human concern is nearly impossible. So I'm drawing this vector v1 here, and I want you to imagine that I've drawn identically the same vector. It looks like I've drawn it pitched up a little bit more, but it's identically the same v1 as was over here. And then to v1, I would add delta v, because that's what my equation prescribes, v1 plus delta v. But I don't know what direction delta v points, so I can't do that. But I do know that when I add delta v to v1, I get v2, which means when I do this graphical addition operation, and to draw the sum, I start from the tail of v1, I draw to the tip of the second vector. So what I'll do is I'll take my v2 vector here and I'll recreate it as well. But and I'll have to make sure that its magnitude and its direction are the same, but I'll draw it. I've tried to make the magnitude and the direction the same, but I'll draw it tail to tail with the velocity vector v1, and so this is the vector v2. Again, returning to the equation, I'm implying that v1 plus delta v is equal to v2. Since graphical addition demands that to add vectors graphically, I put them tip to tail and draw from the tail of the first to the tip of the last, the change in velocity vector must point in this direction, delta v. Such that now what my triangle says, starting at the tail of v1, is that the vector v1 plus the vector delta v is equal to the vector v2, and I've drawn the direction of the delta v vector. Saying it in words is insufficient, but these are the words. The vector quantity delta v points in the direction of change when v1 changes to v2. It still is extraordinarily abstract. I'll make it less abstract by creating two new vectors, different vectors. Imagine that I have a vector that I call v3. and I'll draw it like this. I seek to clarify my point by drawing a vector v4 that's not so different. You see, the change from v1 to v2 was a very dramatic change. I always find insight when I say, let's not let the change be so big. Let's let it be small and see what happens. So imagine that my next vector v4, which I'll just go ahead and draw tail to tail, that my next vector v4 is not that different. You can see from the way that I've drawn it that I didn't change the magnitude too much. But I did change, and I changed the direction just a little bit downward. What is the direction of delta v? Delta v is from the tip of v3 to the tip of v4. That is the delta v vector. When I draw it like this, it makes a little bit more sense visually, I think. Here's v3, and it's off at an angle slightly above the horizontal, and then it turns into v4, which is slightly below the horizontal, and the direction of change is roughly downward. That is the best you're going to do for making sense of this idea of the change of a velocity vector. That the change of the thing is approximately downward, as I've drawn it in that diagram. Pardon me for a moment. I capture a photograph of this so I can get the digital version later. That is a very sophisticated idea that doesn't find its way into practical use for problem solving very often. It doesn't work into problem solving very often, that idea of the graphical representation of the change in velocity vector. But it does help me to explain the direction of that vector when I'm in the middle of some sort of derivation, when I'm explaining some more sophisticated motion. So I may come back to this idea as a mechanism in a derivation to make it clear that the quantity that I'm tracking down in some sort of sophisticated thing that I'm doing is the correct one, describing the nature of things. Very often when I consider the direction of the acceleration vector, I'm doing it in one dimension. I can have a displacement in one dimension that is positive or negative. I displace in the positive direction or I displace in the negative direction. I can have a velocity in one dimension that is quite simple. I'm either going in the positive direction or in the negative direction. Acceleration in one dimension is simple, much simpler than this elaborate description I've had to do just now. Acceleration in one dimension is just as simple. Positive acceleration means that the change in velocity is positive in one dimension. Negative acceleration means that the change in velocity is negative in one dimension. Therefore, if I have a positive velocity and it becomes more positive, I have a positive acceleration. If I have a negative velocity and it becomes more negative, I have a negative acceleration. However, if I have a positive velocity and it becomes less positive, I have a negative acceleration. If I have a negative velocity and it becomes less negative, I have a negative acceleration. That's 4 different descriptions. Now, after many, many years of teaching physics, I've found a way to sort of summarize that. The thing that we say is same sign speeding. It's kind of like a mnemonic. It's a half-assed mnemonic. Same sign speeding. If the velocity and the acceleration have the same sign, then you're speeding up. If the velocity and the acceleration have different signs, then you're slowing down. Same sign speeding. What you must avoid is the terrible, terrible trap of positive acceleration means speeding up and negative acceleration means slowing down. That is not true. The trouble is, it's often true, and the reason why is quite simple. When we solve problems of physics, we very often draw the positive direction of our coordinate system in the direction that the thing happens to be going. And when you do that, in most of the problems that you solve in that context, it will turn out to be true that a positive acceleration will be used to describe a thing that is speeding up, and a negative acceleration will be used to describe a thing that is slowing down. It just works out that way. Do not get caught in that trap. A positive or a negative acceleration needs to be considered in the context of what's happening. Now, later on, it's one of the quirks of teaching and talking about physics. Later on, the whole problem will clarify itself because we'll identify that there are certain natural constraints or conditions of nature that are the cause of the acceleration. And those constraints are themselves vectors, and the whole thing will resolve itself. But for now, please consider that in one dimension, the sign of the acceleration has that little bit of sophistication to it that I need to. I have to this point only considered the acceleration on average. Here again, the acceleration is equal to the change in the velocity divided by the time, where the change in velocity and the change in time are both considered as large intervals, large in the sense that they are easily observable by measurement. I would like to describe an instantaneous version of the acceleration. As a matter of fact, the instantaneous acceleration is more useful to me. It's more precise, there's more information, there's more to explore, there's more to do. And what I'll do is quite simple. I'll recall, just a little bit of a review here, that, my review was already written in the summary here, that I define the velocity as the change in position over the change in time. And I simply converted that average rate of change into an infinitesimal rate of change by a feat of calculus. So what I'll do here is say that the acceleration is the instantaneous acceleration is by definition dv dt, where the use of the lowercase d again implies an infinitesimal change in velocity that occurs in an infinitesimal change in time. Now, I could draw a bunch of graphs right now. I suppose you might say I'm not in the mood. I would show a graph of velocity as a function of time and indicate that on average I describe its slope, and that slope precisely describes the acceleration when I make the interval small. It's exactly the same argument that I made for instantaneous velocity, instantaneous acceleration. Notice a curious thing. This is really just an idea of notation here that I'm adding in for fun and my own interest. That the velocity itself is defined in terms of a derivative. So dv dt is the derivative with respect to time of the derivative of position with respect to time. What I've effectively done is taken two derivatives. I had my position, I took its derivative with respect to time, and I got velocity. I have the velocity, I take its derivative with respect to time, and I get acceleration. And I think immediately in that moment you realize that this process goes on ad infinitum. I just keep taking derivatives over and over again and find successive rates of change one after the other. For example, the derivative of the acceleration with respect to time, in fact, has a name. It is called, does anyone know? Yes, the derivative of the acceleration with respect to time is called the jerk. The derivative of the jerk with respect to time, I don't know, is anybody aware? It's called the snap. It's in fact called the snap, the derivative of the jerk with respect to time. Now, I know if you take successive derivatives, they have other names, and I don't know if anyone has looked into that and can name what comes after the snap. I would be shocked. I'm sorry? It's called crackle. Crackle. It is actually called crackle. They're crackle and pop after that? And then what? And then lock and drop. So we've got jerk, snap, crackle, pop, lock, and drop. Okay, so do I have need for these successive derivatives? Well, it turns out that perhaps in an engineering context I have use for the jerk. And we use it in common language, don't we? Because we might say that we were all enjoying a day at the amusement park and we got into the roller coaster, and then when it began to move, we all jerked to a start. Well, because the acceleration is zero, and then the acceleration changes to some other acceleration, and so there is a change in acceleration in that moment. So I can imagine the jerk being a useful quantity. And then the rate of change of the jerk, where is that in the experience of that or the dynamics of that? So in an engineering context, these successive derivatives might come into very obscure use, but we are content to stop here with the derivative of the velocity with respect to time is the instantaneous acceleration of the motion. So I'm taking the derivative of a derivative, and that's okay. I can take successive derivatives in this way. There's a notation that is sometimes used for this, and I warn students about getting too wrapped up in notation. When I discover new notation, what I should do is consider the meaning of that notation behind it. What does it mean? And then simply become comfortable with how maybe the person who invented the notation created a notation that sort of has the feel of it. And in this case, I believe that it's so because this could be written as the second derivative of the position with respect to the time squared. The second derivative of the position with respect to time squared. That's just notation. There's nothing special about it. And in fact, it's inconvenient to write all of those second derivatives. So in physics, we have a notation that we commonly use to ease the notation, to make it quite simple. And you are welcome, as a student of physics, to use this notation all the time. An X with two dots on it. The dot above a quantity in physics implies the rate of change of that quantity specifically with respect to time. Now, those of you who have studied some calculus in mathematics know that in mathematics it's common to describe a derivative with respect to x with a prime. That is, if I have a function of x, then that is f, then f prime is the rate of change of that function with respect to x. We have other uses for primes in physics. So in our calculus of physics, we not always, somebody out there is breaking the rules, but typically we don't use primes. But when I see the dots, x double dot, I identify as the acceleration. As I say, as students, more advanced students of physics, you are welcome to do that. Following along with the notation, it is also true that x dot is equal to the velocity and that x, quite naturally, is equal to x. So these so-called kinematic quantities, position, velocity, and acceleration, can be described in terms of this dot notation, with the instantaneous acceleration being described here with a double dot.